So in this problem, you can see we want to determine the maximum shear at C, and C is a little off-center here, for this scenario of moving load. So I'm going to move from the right side to the left side, some kind of odd-looking truck contraption here. So the first thing we need to do is what? In all these moving load problems, we're trying to find the shear at C, so we should probably draw the influence line for the shear at C. So I'll do that first. Remember, the way we do that, using the Mueller-Breslau principle, is I will imagine this shearless connector applied at that part of my structure. I do have a pin here and a roller at B. Now remember, what we're going to do is on each side we would imagine positive shear being applied, and then what do? We look at how that particular structure would displace. So looking at the left-hand side from A to C, you can see at C on the left side it's going to move up or down. It's going to move down, so that would be the shape there. And on the right-hand side, what's going to happen at C? Up or down? It's going to move up. So I know that this is roughly the shape of my influence line. So let's redraw that. Remember, this is the shear at C. So as the moving load moves as a function of x. So remember, these slopes are the same. So if I'll draw this, and then I'll slide my line up, and I'll get this. So that's to scale, or to some better scale, what my influence line looks like, and the qualitative shape of it, which we get that from Mueller-Breslau. And remember that this distance is 2 meters, and this distance is 6 meters. So now, how do I establish these heights? Well, remember, the triangles are similar. So basically, this height, the negative value, is to 2 as this height is to 6. So that tells you right away that this height is what? 3 times bigger than that height. So that means if I add 3h plus 1h, I get 4h. And we know that this difference has to be 1. So that makes this top value what? 3/4. And the bottom value, -1/4. Everybody see that? Do I need to be more formal with that? So you can see that this height is 3 times this one, because the base is 6 is 3 times bigger than 2. That's a great thing about influence line for shear. There's no work. It's just, there it is. The work was here in Mueller-Breslau to get the shape, and then remembering that at that position, the change in shear is 1, and using that to your advantage. Okay, so now with our influence line, what do? We're going to let our moving live set of axles or loads start on the right-hand side and move to the left. Now we're trying to find the maximum shear created. Just looking at it and observing that there's a lot more positive shear than negative shear. So I'm not even going to look for the negative value, since it's going to be such a small contribution. So I'm pretty much going to be able to observe from the graph that positive is going to be the way to go. So when I move my 3 loads from the right side to the left side, I'm always going to stop them on the big, just to the right of C, and not just to the left. Okay, so how many cases will we have with 3 loads? 3 cases. So let's go through them. So I'll start with, let's see if I can squeeze this all in on one page. So I'll try to start case 1 up here. And what I'll do is I'll quickly try to resketch my influence line for the shear at C. Just to give you kind of the rough shape. And then we're going to roll over our load. So the first load is going to start on the right side and come over. That's our 1 kilonewton load. So it's going to land right about here. And then 1 meter back will be my second load, which has a value of 4 kilonewtons. And then 3 meters back, I'll have my third load, which is the largest of the set, 3 kilonewtons. So now I'll need to project those positions down onto the line and come up with values for these points. We know this point from our work over here. This is going to be 3/4. What are these values? Well, what's the slope of this line? Rise over run, right? So that's 3/4 divided by 6, which is what? That's 1/8, isn't it? 3 divided by 24 is 1/8. So our slope is 1 to 8. So every foot I move to the right, I drop 1/8. That make sense? So I move I said foot, but so I move 1 meter, I drop 1/8. This is 6/8. Dropping 1/8 gives me 5/8. Moving 3 more meters drops 3 more 8s, brings me to 2/8. You guys get those values? So now, the shear at C for case 1, I'll just do my accounting. So I take the first value, which is 1 kilonewton, times 3/4, plus 4 kilonewtons times 5/8, plus 6 kilonewtons times 2/8. What's all that equal to? I can't do that very quickly. What'd you get?
4.75.
Anybody else get 4.75?
Yes, 4.75.
So 4.75, and that'll be kilonewtons. Does anybody have any questions about that? Because all we're going to do is do it 2 more times and then pick the largest result. Of course, in the second case, we're going to let the loads continue to move to the left, and the second load will go to the highest point, and then the third case will be the last load will go to the highest point. Of course, these first 2 move over to the negative side are potentially off the structure. Okay?
So what do you do with that?
It's off, it's off. So let's see what happens. So let's go to case 2. I mean, you can think of a large... I was actually looking at something yesterday with one of our graduating seniors about doing live loads for locomotive traffic. And if you imagine what a locomotive looks like, there's multiple contact points. And you ought to see the AASHTO code for locomotives. It's, I think, 16, potentially 16 moving loads to model a locomotive. Anywhere between 3 to 4 to 5 feet apart. So you can imagine doing a scenario like that, it would have 16 cases. That's the job you give to your day 1 rookie engineer, just to keep them busy. Keep them out of your hair. Obviously, there's programs that would make small work of that, or a chart or an equivalent, but still, kind of interesting that they're still doing it that way. All right, so let's go back, and just to help you visualize it, again, I'll resketch the influence line for the shear at C. And this time, I left this off last time, but I think it's important to put it on this time. These were the I'm sorry, that's a 2. This is a 6. So again, this is going to be 2 meters and 6 meters. So now I'm going to let the second load come to the top. So that's my 4 kilonewton load. Of course, now 1 meter in the front is the 1 kilonewton load. And this is 2 meters, so I'm okay. I'm still on the structure. And then 3 meters back is the larger value, 6 kilonewtons. So again, I'll project those coordinates down onto the influence line. Remember that I already know this one is 3/4. I already have the slope of this side. It's 1/8. So I move 3. I drop 3/8. So 6/8 minus 3/8 is 3/8. That's a mouthful. And now what's the slope of this line? Remember, the slopes are the same, but even if you check it, rise over run, it's still 1/8. So if I move 1 meter forward, then I'm going to go from negative 1/4, which is 2/8. This will be negative 1/8. Everybody see those values? So once you have the geometry, now you can do the calculation. So the shear at C for case 2 would be 1 kilonewton, but it's now multiplied by negative 1/8 plus 4 kilonewtons times 3/4 plus the biggest load, the 6 kilonewton force, times 3/8. What's that going to be? I think it's going to be less than 4.75, but I'm just guessing. Maybe I'm wrong. I'm wrong. This will be 3, and this will be about 3 something. No, this will be bigger. Like 5 something? 5.1. 5 and an 8?
Yes.
I'll write it that way since I'm running out of space over here. Sorry about that. So that seems to be the biggest one so far. We got to do it again, though. So finally, case 3. And again, to help you visualize it, I'll redraw the influence line for the shear at C again. And now we'll let the last load in the sequence come to the top. So that's our 6 kilonewton load. And then 3 meters in the front is the 4 kilonewton load, but it's left the building, right? It's driven off the end. So in this particular position, only the 6 kilonewton load is on the structure, the last load. So that'll be an easy calculation. We know the height there is 3/4, so the shear at C for case 3 is just 6 kilonewtons times 3/4, which I believe is 4.5. So now we know that the maximum shear at C for this particular case would be this value, which is 5.125 kilonewtons. So any questions about that? If you can master this particular skill of, well, actually 2 parts. If you can draw a correct influence line. Obviously, if you draw the wrong influence line, you've made a wrong turn. I will still look and see if you understand this part, so I won't crush you. But yeah, you can see it won't turn out very well. So focus on this, and then after this, it's just really a little bit of bookkeeping. If you can pull off one of these, I could, like a problem like this, I can set this up so that maybe some of them aren't so much work. Any other questions about that? Obviously, in practice, you would have, like I mentioned before with locomotives, you could have multiple loads. Even with a modern tractor-trailer truck, you're looking at 5 contact points. And then, of course, you could have a truck behind a truck, behind a truck, behind a truck, behind a truck. So the maximum design, if you're worried about this sort of thing, is really fully loaded transport trucks, head to tail, going well over the speed limit. So you have impact and really max. And all that is still factored up so that you're really designing for much more than that. And of course, your structural strength is reduced. So we have a lot of factor of safety built in. So even though you think we can't do it, a lot of times we can. In fact, the state has a permitting office that allows you to go across a structure with extra wide load or extra heavy load as long as you get a permit. And if your loads get really, really heavy, obviously they'll check to make sure the bridge won't just die underneath your feet. But if it gets really, really heavy, the state figures, well, that's going to shorten the life of the structure, and the cost of your permit can get quite high. And those permit fees supposedly are collected into a fund that would then repair the structure. That's officially the rules. Whether that's done or not,
Politician's pocket.
yeah, it's just like your Social Security money. It's there.
If that were a moment, how do you determine the height for your moment when you use the dress file principle?
You remember, you have to go back and do that one case with the determining the moment at that high point. Right? You're right. That's an interesting point. Let me stop this one and we'll talk about that for a second. Okay.